All right, let's go ahead and get started. What I'd like to do first is go over some logistics of the quiz that most of you got back. First of all, I want to let you know that my TA grades the quiz. The TA only grades the quizzes, so if you still have questions about content and stuff, you need to ask me. The way I did this with the quiz was I wrote out all the answers that I thought were possible so that she would know what's acceptable. She even caught that I wrote one down that was the wrong answer, so we fixed that and didn't mark all of yours wrong because I made a mistake. So if she had any questions about whether something was an acceptable answer, she emailed me or we talked and we worked it out whether it was okay. So if you still have any questions about any of the answers you gave, feel free to come up after class or contact me by email and let me know what it was. A couple of other things about the quiz. If you had a 9 or 10, you're doing fine. Keep doing what you're doing. If you got an 8, you might want to sort of fine-tune your studying strategies. And if you got anything below an 8, you should really figure out if you did study, if you didn't, how you studied. Try to figure out where the breakdown happened, because it's sort of like a GPA. Once it gets low, it's really hard to bring it back up again. So try to problem solve now. I'll be happy to meet with you and talk about how you're studying. If you ever have concept questions, try to bring them up in class, because usually if it's not just you who has the same question in concepts. So we want to clarify as much as we can as we go along. Any questions about the logistics of the quiz? Okay. All right. Any questions from last time? We were talking about pulmonary subdivisions. Everyone's resolved not to be couch potatoes, go swimming, have great vital capacities. Inspirational, huh? All right. Okay, so what we're going to talk about today gets a little bit trickier in some respects in terms of concepts. So again, if at all possible, try to ask questions as we go along. We're going to start with a few definitions of some things that we measure in speech production. One of the things that we measure that actually gives us a lot of information about how we use air when we talk is air pressure. And air pressure is just the force per unit area acting perpendicular to a surface. And I can never picture it that way. So what I usually picture is a pressure transducer, which I'll bring up again. If I were measuring pressure inside my mouth, I would put this little sensing tube in my mouth and go pa, 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 and it would tell me the pressure I'm generating for the p sound. Okay? So it's how much force is acting upon the pressure transducer that's in here that's being sensed by this, that's perpendicular to the flow of air. Okay? You don't need to know all the details. Just know that it's a force per unit area acting perpendicular to a surface. And we'll talk about the ones that we care about, because there's only a few pressures that we care about in speech. Alveolar pressure sounds like it should be pressure at the alveolar ridge, but it's not. It's one of those terribly synonymous terms. It's actually pressure in the alveoli, or pressure inside the lungs. That's not something we measure directly. Subglottal pressure is also an estimate that we don't measure directly. And when we get to laryngeal function, we'll talk about how we're able to measure or estimate subglottal pressure. The one that's the easiest to visualize is intraoral pressure. And intraoral pressure is just the pressure that you build up in your mouth, inside your mouth when you're saying a sound. So what kinds of sounds are characterized by intraoral pressure that we might be interested in measuring? Stops or plosives. So we know that for a plosive, we need to impound air somewhere. So we have to create an occlusion, we have to build up air pressure behind that occlusion, and then we release the occlusion to make the plosive. So intraoral air pressure can be of interest to measure in some populations. What do you think could cause reduced intraoral air pressure? Say most people are saying a pa, 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 pa. What would cause someone to produce an intraoral air pressure for a P that would be less than normal? Oh, good, you're remembering. Go for it.
A cleft lip.
Cleft lip, yeah, that'd be an extreme case. So a cleft lip that wasn't repaired, that means that you couldn't seal around the sensing tube. So you couldn't produce bilabial closure. What are some other examples? Go ahead.
If they have weak musculature.
Yeah, if they have weak muscles. So sometimes if there is a weakness around the lips, people are not able to close completely. And what kind of sound do you think you get if you're trying to make a plosive but you can't close completely? What would that p turn into? Oh, you guys are off. Good tries, but not quite. Think through it. Try to do a p without closing your lips all the way. Go ahead.
Would it be a fricative?
It would be a fricative. You end up with a bilabial fricative, which doesn't exist in American English, so it doesn't help them any. So the bilabial fricative, or just air flowing through that constriction that should have been closed at the lips. So, so any kind of bilabial lip weakness, any kind of cleft that may make it impossible to close the lips. What else could cause reduced intraoral pressure? Go ahead.
Would Bell's palsy cause it, since it's numbness on one side of the face?
If it's more than just numbness and actually paralysis, it could. And if it's unilateral just on one side, then it would only be one side that would have some air escaping. And sometimes people can compensate for that. You know, it's unusual when you're trying to close your lip if you have unilateral paralysis that there's like a big gap on the one side. Usually it sort of follows along with the other one. Yeah.
Like a inefficient velopharyngeal seal, like if they've got air going up through the nasal cavity.
Yep. So if you're not closing off the velopharyngeal port, you're not able to build up that air pressure in your mouth. So that's where it's going to sound like an M, or more like nasal air emission on a P, like a where you have air escaping rather forcefully out of the nose when you should have had that tight seal. Okay, so the people that were able to measure intraoral pressure and the ones that will give you a valid measure are people who are actually able to close their lips. Okay, so intraoral air pressure is fairly straightforward to get. Intraoral air pressure is measured, the unit of measurement is centimeters of water, which always seems strange to me for air, but it's based on a U-tube manometer. So remember last time when we talked about the need to calibrate instrumentation. Every piece of instrumentation has a specific calibration device that you use with it. So with the pneumotachograph rope, I should change that, to calibrate for volume, you use a known volume like that 3-liter syringe. To calibrate for air pressure, we use a manometer, specifically a U-tube manometer. And we'll see a picture of this in a video in just a little bit that will clarify it even more. But you're really talking about how much force it takes to displace a column of water. And that's why it's measured in centimeters of water. So I could put my lips at the end of the tube on that U-tube manometer and go, and I would see how much force, how much fluid was displaced when I built up the pressure for that P. And you would measure that, and you would say, okay, I had 3 centimeters of water pressure built up for the P production. Okay, so when you're thinking about the gold standard or what to calibrate with, for a pressure transducer, you calibrate with a manometer. So the pressure transducer is actually a fairly simple little device. This is an example of one. You can see that it's not very big. And this is the pressure transducer itself, which isn't going to do us much good because we have no way to connect it to the airway at all yet. So that's why we attach a sensing tube to it. And the sensing tubes don't really get in the way very much for the kinds of tasks that we do. So usually somebody's doing like a pa-pa-pa, and the tongue tends to stay out of the way. So a pa-pa-pa-pa-pa, it's sensing the air pressure I'm building up for the P. And inside this very small metal portion of the pressure sensing tube are a series of wires that are strain gauges. And strain gauges bend really, really easily. and strain gauges have a current going through them. So as they bend, don't worry about the details of this. Don't even take notes. I just want you to get the basic concept. You got a little bendy thing in here, okay? So you have like a very flexible, picture it like a diaphragm going across. Little flexible seal going across that has wires going through it. That moves, and as the current's going through the wires, when you displace it, so if I'm going, I'm pushing it that way, that's going to change the resistance to the current going through the wires. And because we've calibrated it, we know how much of that is going to correspond to a voltage output. Okay, so I already connected this to the YouTube manometer, and I displaced the water by 5 centimeters. And then I looked at how much the voltage changed coming out of the strain gauge. So then it's calibrated. I know, okay, when it goes this high, that's 5 volts. And any time after that, when I go pa, I can have the actual pressure generated in centimeters of water. Okay, so you've got a little electronic circuit going on in there. You've already calibrated, so you know what the voltage changes correspond to in terms of air pressure. Making sense? Questions? Yeah.
Make a difference the length of that tube coming in there? Because isn't it?
Yeah, that's a good question. You always try to keep tubing short and unkinked, because that really screws up your measurement. Yeah, you try to keep it short, and in most cases it's fairly straightforward. But you always want the minimal distance between the sensing, where you're sensing the air pressure in the actual device. All right, so that's how we do pressure with a YouTube manometer for calibration. There's a number of positions that can be used for a pressure transducer where the sensing tube is. This one is a kind of strange one that people did maybe in the 50s and 60s when they were trying to figure out some basics, where the sensing tube is actually curved around the back molar. What sound would that give you the pressure for? What plosive could you find out about if you had it way back there? Ka, right. Ka is really hard to get. If I have the pressure sensing tube here, where I would for a pa sound, it won't tell me anything about what's going on for the ka because the occlusion is way back here. And you have to sense the pressure right behind where the occlusion is. Okay, you have to sense it right where it's being built up. So you can imagine for subglottal pressure, that presents a little bit of a problem, because sensing the pressure directly would be right down here. And we'll talk about how you work around that in a bit. So this is an atypical location for a pressure sensing tube. Most of the time we're measuring intraoral pressure. It actually gives us lots of good information, both about the ability to implode air for plosives, as well as some indications of laryngeal function that we'll get to when we get to that section. So airflow is another measure that we're interested in terms of the aerodynamics of speech. And it is how much air moves through a given space in a certain amount of time. And you can really picture this just in terms of picturing how you'd measure like the flow of a river. Our bayous don't flow. It has to be a river. So you can't have mold and alligators and all that. So you've got a rock that you're looking at. And to measure how quickly the river is flowing, you would have a way to measure flow past the rock. How much water went past the rock in a certain amount of time. So we're measuring how much air goes past a certain point in a certain amount of time. Airflow is measured in cc's per second. We mentioned that last time we met. 1,000 cc's in a liter. We measure airflows in how many cc's of air go past a certain point in a second. And for speech, we can be talking about some fairly large numbers. So the typical airflow, for example, for the air going past my vocal folds in a normal voice quality is probably around 100 to 150 cc's per second. If you're looking at nasal airflow in normal non-nasal sounds, it should be 0. Okay, you should never have any air coming out your nose when you're not doing a nasal sound. If a person is breathy and kind of sounds like this, they have lots more air flowing through the vocal folds. That can be like 300 cc's per second. So now you picture this in terms of people who have muscle weakness, maybe not a lot of air to work with. Then as soon as you have inefficient valving, we think of like the vocal folds and the velopharyngeal port and the articulators as valves. They're valving the flow of air. As soon as you have inefficient valving, you start wasting tons of air. And you end up with things like short phrases. People have to compensate for that. You can also have an inefficient valve at the velopharyngeal area. So the person sounds like this. And that can be like 100 cc's per second. So seriously, and you have people with head trauma who have screwed up all of their cranial nerves. They have inefficient valving here, inefficient valving here, and they can be wasting 300 cc's per second of air. So it's a fairly large portion of the amount of air that they would be breathing in. And one of the things that we do in treatment to see if it's effective is we can measure airflows from different areas. So I can measure nasal airflow on someone, and then I can see if the treatment that I've used is cutting down on that nasal airflow. I can measure how breathy a person is in terms of how many cc's per second is flowing through the vocal folds. And then I can see if treatment to reduce breathiness is having an effect on that. So that's one of the reasons that we want to measure airflow. And we do that with a pneumotachograph. And I know we used this to measure volume the other day, but it's actually a pneumotachograph. And we used it to measure volume because we integrated the air flowing through it. So the software that it was attached to integrated the air flow and turned it into volume for us. But when you think about measuring airflow, think about a pneumotachograph. Think about how to spell it. Because it doesn't sound good if you go the thing that's used to measure airflow. But as I recall, I never asked on a quiz for you to spell that because I didn't want to see what the options were. Now we don't have, you'll see in the video we're going to watch, the device that's used to calibrate a pneumotachograph is a real pain to do. It's a glass tube with a little ball that floats in it, and you connect it to compressed air. You turn on the compressed air canister, hope it's not going to shoot all over the place, and you adjust it so the little ball is floating in this glass cylinder at like 100 cc's per second or 200 cc's per second. It's really a pain to calibrate. And you'll see that in just a minute. That device is called a rotometer. R-O-T-O-M-E-T-E-R. A rotometer. So the rotometer is what's used to calibrate a pneumotachograph. Any questions on airflow? Yeah.
How did you define valving again?
Valving is sort of the regulation of air flowing through the vocal tract. And a lot of people think of the speech production system as a series of valves. The first valve is at the level of the vocal folds. The next valve is at the velopharyngeal port, and then you have a valving of the articulators as they're moving too. So all of that is modifying and regulating the air that's going through the vocal tract. Other questions? Okay, so volume, here's where I never want you to think of as volume as the knob you turn on the radio anymore, or how loud somebody's talking. Volume is the amount of air that's in a specific space. Okay, so just think now of volume as a quantity of air occupying a space. So we can measure lung volume. We can measure how much air is in the lungs. And we've already mentioned that it's possible to integrate airflow to get volume, which is a much less, it's an less unwieldy? Yes, less unwieldy way to measure volume. So what I'd like to do is play a video that kind of, what is that? That sort of reviews the things that we just talked about.
laboratory here at the University at Buffalo. We collect aerodynamic as well as respiratory kinematic data produced during speech. Our primary goal is to describe and investigate children's speech mechanisms with an emphasis on the laryngeal and respiratory systems. In order to do this in a relatively non-invasive way, we use several sensing devices that the children really tolerate quite well. The first device is called a pneumotachograph mask and is used for sensing airflow. This particular mask design can be described as being circumferentially vented and was developed by Martin Rothenberg at Syracuse University. As you can see, it's made from a standard respiratory face mask which has a series of holes punched around the circumference of the mask. The holes are covered by a fine wire mesh, and that presents the slight resistance to the flow of air through the mask. The resistance causes a pressure differential which is proportional to the airflow through the mask. Right here is a pressure tap that's also a port to the air pressure transducer, which is mounted right on the mask. This particular transducer has a wideband frequency response in that it picks up higher frequency flow components than most typical air pressure transducers. It's because of this response that it produces a waveform that looks very much like a voicing waveform. Notice that we have a second pressure tap which leads to a second transducer with a lower frequency response. It's from this transducer that we generate the average airflow and the volume waveforms. The third tap on the mask right here is connected to another pressure transducer optimized for measuring intraoral air pressure. Inserted inside the mask at this tap is also a small hollow polyethylene tube that will be placed into the oral cavity and picks up the intraoral air pressure values. Now I'm going to demonstrate how we calibrate for airflow, air pressure, and air volume. To calibrate for the airflow, we place the pneumotachograph on the mold. While using a device called a rotometer to indicate the flow moving through the mask transducer system, we record this signal and use it for later reference. We calibrate for airflow for each mask size that we use. So this is the medium-sized mask, and this is the one that's used for adult females and teenagers. We use the large-size mask for adult males, and this is the small-size mask that's used for the younger children. When calibrating for intraoral air pressure, we use a device that's referred to as a U-tube water manometer. By displacing the water column and measuring the distance that the column moves on each side, we can express the subsequent pressure measurements in terms of centimeters of water. We record the calibration signal produced and use it for later measurement. Our next calibration procedure is for making the volume measurements. By not having our subjects breathe into a respirometer to calibrate for volume, we don't fatigue them with an additional calibration maneuver. This has been especially helpful when working with the children or with hard-to-test patients. This time we connect the mask on the mold to the respirometer, and we repeatedly displace 2 liters of air through the mask. We digitally integrate this cyclic flow signal and then scale our low-frequency flow channel. This allows us to calculate the volume displacement by integrating the flow signal. This brings me to the last piece of equipment that I'd like to demonstrate, the linearized magnetometers. This is just a brief deviation from the aerodynamic techniques that I've already presented. But since we use this quite typically with our aerodynamic techniques, I wanted to present it at the same time. The magnetometers have been used for quite a while, and you can look at Hickson and Hoyt-Hickson for further detail. Linearized magnetometers operate in pairs. There are 2 pairs for sensing the chest wall movements, one for the rib cage and the other for the abdomen, so that when attached to the front and back of the abdomen, they will track the movement of that part of the chest wall. Here, I'm just going to demonstrate the movement of the abdominal pair. The emphasis on this demonstration so far has been on speech aerodynamics, and now I'm briefly going to demonstrate just how we collect the simultaneous respiratory kinematic data from unwilling but well-paid children. Here's a segment from a tape made of Nick, my son, performing the pa, pa, pa task. We've already attached the magnetometers to the chest wall. We've got one pair attached to the rib cage.
We all use our kids.
And the other pair attached to the abdomen. Turn around, Nick, so that we can look at that.
We'll get your
right,
magnetometers
now turn
next
around
time.
this way. And what we're going to do next is have Nick sit in a chair, and then we'll look at how we pair the aerodynamic equipment with the respiratory kinematic equipment. We're ready to put the mask on Nick. Before we start, I'd like to point out that we've got this part of the mask which would hit the bridge of the nose built up with a little bit foam on the inside, because very often we get a leak in this area, and we want to make sure there's not a leak during the task. Okay, Nick, I'm going to put this on your face. I'm going to kind of smush it on hard, and then I want you to put the tube in your mouth like you would a straw, right behind your lips and behind your teeth, and then you'll just talk around it. And you're going to say that pa, pa, pa task for me, okay?
All right.
Okay. Ready? Go.
Pa, 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 pa.
Okay? Okay. You're going to say 7 of those. I want you to make them all connected. And I want you to make a nice pa. Not a ba, but a pa. Okay? Ready? Go. Pa, 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 pa. All right. At this point, we would work with the subject. We would make sure that the number of syllables were the correct number, that there was a tight seal around the edge of the mask. Let me just take this off. That we had appropriate pressure waveforms, and that generally things are just the way we want them. We try to get 3 trials for this particular task. Then if we wanted to do some inverse filtering, we might have Nick phonate an ah or an ah and look at inverse filtering during a sustained vowel. And all the while that we're collecting the data, as I said before, we'll check for leaks and for the appropriateness of the task. And that's it. Now, let's take a look at some of the waveforms that were produced by that session. The first waveform is the wideband airflow signal, which includes voicing.
That gets way ugly.
She held it on him pretty tight.
Oh, you have to. So why do you think you need to hold the mask on so tightly?
Air, so it doesn't leak.
So it doesn't leak. Yeah, if you're measuring airflow and you have a leak, your values are just all wrong. So it has to be on fairly tightly. And I've done this with singers, and I let a number of them put the mask on themselves, and I got really, really low airflows for one of the tasks, which was soft, I think in their chest voice, a soft, low sound. And they were producing like 40 cc's per second, which seemed just ridiculous to me. And so I brought one of them back, and I said, I have to do this again because I just don't believe that the values are right. And I squished the mask on her face, and I said, does that feel tight? She said, oh God, yes. So it was really a tight seal, and we repeated the task, and it was still 40 cc's per second. So, which made me figure out how she's regulating airflow on a really, really soft task. So most of us, when we do something softly, would go pa, 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 and be really breathy, right? She was doing pa, 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 and keeping the vocal folds completely adducted at the closed point, and just using tiny little bit of airflow to go through them. So it was valid, but I didn't believe it until I redid it again because I thought for sure it was leaking somewhere. So you always have to double check that, and that was a really good point in the video in terms of how careful you have to be to smush the mask on. It works fine with your own kid, but you can get paid subjects to do it too. The only thing she didn't demonstrate that I always do, and when you become clinicians, you really need to think about this. Whenever you ask a client to do something, you should follow it up with like this, and then demonstrate it. You know, she was doing the task simultaneously with her kid, but that's not nearly as good as going, okay, this is how I want you to do it. Just watch for a second. pa, 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 like that. And then they'd have it. So never expect that you're just instructing someone is going to get them to do the task right. You need to show that you're willing to do it too, because some of the things we ask clients to do are kind of weird. And you need to demonstrate the right way to do it. I wanted to show you one other kind of mask. This is a version of the Rothenberg mask that also is designed to minimize rebreathing of carbon dioxide. It has these little vented mesh areas in it. And this one is specially designed. It has a bridge between the nose and the mouth. So in this way we have an airflow or pneumotachograph here, another pneumotachograph here. And this way we're able to tell how much air is coming out of the nose and the mouth simultaneously. Okay, so if it's divided off like that, you can get ratios of nasal to oral airflow. So people do lots of customization with the masks. The way that she calibrated the volume was with the old-fashioned spirometer, that inverted cylinder on water going up and down. And so she knew that she was displacing 2 liters of water by looking at that charted output. So what else would she have needed to calibrate for the setup that she showed us? There was one thing that she didn't show the calibration for because it's a real pain to do. The magnetometers. Remember at the end she showed those little discs, the magnetometers? They're used to relate rib cage and abdomen movement. We'll get to this another time. Don't worry about the details. They're used to relate rib cage and abdomen movement to the volume of air that's exchanged. So somehow you have to relate that displacement to volume. Most people do it by having a person breathe in and out of a plastic bag that holds exactly 1 liter of air. It's really strange. And they're called spiro bags. And so they're on a little cardboard tube, and it looks like a baggie that you're breathing in and out of. And if you just breathe in and out of that, the experimenter knows that they've displaced 1 liter of air. So some of the calibration maneuvers get a little odd. Any questions on calibration? Yeah.
Okay, when we were watching the calibration, I think she was doing the YouTube
Manometer.
Yeah, I was confused as opposed to like what you said before we watched it. I thought it was a way of measuring I didn't know it was a calibration. I just thought it was another device used to measure the airflow.
The manometer, think of manometer related to air pressure. And you could use it to measure air pressure directly. Like you could have somebody put their lips on the end of it and go pa, pa, pa. But it's really, really hard to read the water as it's being displaced quickly. So a more sophisticated way to do it that you're not relying on just eyeballing where the water level is to actually use the pressure transducer that you calibrated using the manometer. So the way you are sure that you have a set displacement is you actually use a little syringe and inject air into the manometer and keep it at like 5 centimeters of water of displacement while it's hooked up to your pressure sensing transducer. And then you've got the voltage output that's related to 5 centimeters of water. So you could use it directly, but it would be, it's just hard to eyeball it. So you typically wouldn't. And then if somebody really screws up and goes pop, 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 the water blow out all over, it's ugly. Other questions on calibration or the devices we've talked about so far? Yeah.
So the YouTube manometer and the pressure transducer work together?
The YouTube manometer is used to calibrate the pressure transducer. So that's really how you want to think of it. The YouTube manometer by itself isn't a really useful clinical tool. So you really need the pressure transducer to measure intraoral pressure. And we use the manometer to calibrate it. Other questions? Okay. I just wanted to bring up a few synonymous terms before we get into passive and active forces. And some of these I don't like, but you'll see them in other other professions' literature. So the term that we typically use for breathing out at rest, the place where you always end up, where the opposing forces of the lungs and the thorax are equal, is resting expiratory level. Pulmonologists will often call that point functional residual capacity, or FRC. You'll never see that in the speech literature, but you will see it often in pulmonary literature. Some people call it the relaxation volume, because if you just relax, that's the point to which the system goes. And the one that does make a little bit more sense is end expiratory level, if you think of that as end of a quiet tidal breathing, expiratory level. Okay, so they're all referring to that same point in our respiratory system. Okay, so I'd like to talk about passive and active forces, and there are a couple of things to keep in mind, again, just in terms of the nitpickiness of how we need to be about terminology. When you think about a passive force for respiration, you want to think about no muscle activity at all. Now, that may be wrong in minutia, but in the big picture, when you think about a passive force, think about the muscles not doing anything and the forces that are acting on the system anyway, without any muscle effort. So passive forces are no muscle activity. Active forces means that you're contracting some muscles to move the system. Okay, so active forces require muscle activity on your part. So I'd like you to think for a second about what the passive relaxation forces are. So if I take a big breath and just let it out and don't do anything with my muscles, what is making the system go back to resting expiratory level without my doing a thing? Yeah.
Elasticity?
Elasticity is one of the number one relaxation forces. Elasticity means that when I move something away from its rest position, it always wants to go back to its rest position. You can think of a rubber band. You pull a rubber band out of its rest position, elasticity makes it go back. If you have young skin and you pull skin up, elasticity will make it go back. As you get older, it goes back less quickly, but there's some elasticity left in there. So elasticity is one of the main forces that requires no muscle effort on our part, that returns things back to resting expiratory level. What else is there? Picture a big giant breath, you let it go. Yeah.
Gravity?
Gravity, yeah, very good. I never think of gravity, but it definitely acts on the respiratory system. Gravity helps move things back down. So we've got elasticity of the respiratory tissues in the lungs. We have gravity. What's the diaphragm doing? You've got to push a button.
It's relaxing.
It's relaxing, right. So again, that's a passive force. Just the diaphragm relaxing. You're not doing anything to control it. It's another passive force that will get the respiratory system back to resting expiratory level. And the other one that I never picture, probably because I never understood it all that well from anatomy, is the torque of the ribs. You know how the ribs flare out a little bit? You guys probably understand that better than I do. They flare out a little bit when you relax, they move back in. That's another passive force. Yeah.
This is kind of out there, but is it because of the pleural linkage, or is that something totally different?
The effect that all of the passive forces have on the lungs is due to the pleural linkage. Yeah, that's sort of always related. So the lungs are affected by all of those external relaxation moves. Everything gets smaller, the lungs have to get smaller along with it. Yeah. Other questions? Okay. So we're going to talk about air flowing in and out of the lungs now, and we have to go back to this concept of air pressure. Same way the gas pressure worked in the alveoli and in the blood vessels. Air is going to move from regions of high pressure to regions of low pressure. If you watch all our crazy weather guys, they like high pressure systems, low pressure systems. They talk about it all the time. Just think about high pressure always moving to low pressure. And now, because we're working with lung volumes, we have to think about the relation between pressure in the lungs and volume. And assuming that everything's equal, which we can because we're going to take sort of a simplified view of things, volume and pressure are inversely related. So as volume increases, pressure decreases. As volume decreases, pressure increases. And I like this example of it. Here, if you picture the same number of air molecules in each of those 3 cylinders. This one you have a large volume for 10 air molecules. That's going to be low pressure. Same 10 air molecules here, the volume gets a little bit lower. And here you have a very small volume, the air pressure molecules are compressed, and you end up with high pressure. So think small space, high pressure. Now this is going to matter when we think about the lungs getting bigger and smaller as we breathe. So when we think about the pressures as we're breathing, the lung pressure is actually the pressure inside the lungs, the pressure of the air molecules that are inside the lungs. And atmospheric pressure is the pressure just out here, outside the body. Okay, now here's where it gets a little bit tricky. So we want to think of 3 different points in the respiratory cycle. And the first one that we're going to consider is when the pressure inside the lungs is equal to the pressure outside the lungs. No air is moving. So first of all, when does this situation happen? Somebody hit the button and tell me. Yes.
Is it at the resting expiratory level?
Yes. One point is at resting expiratory level. So you've reached that point where the opposing forces are equal. Everything's in balance in the respiratory system, and there's no air exchanged. So lung pressure equals atmospheric pressure. And that's the easiest one to think of. Okay, just think of resting expiratory level being the point where lung pressure equals atmospheric. Now, the tricky thing about visualizing what happens as you're breathing is you have to picture this during the act of inhalation. It doesn't work if you picture it like at peak inhalation. Okay, you have to picture as the lungs are getting bigger. Okay, so we know that when we breathe in, the diaphragm flattens, the external intercostals contract. Both of those actions gradually increase the volume of the lungs. Okay, so you're gradually making the lungs bigger. So as the lungs get bigger, there's more space in them for the air molecules. So relative to atmospheric pressure, as you're breathing in, pressure inside the lungs is negative. Okay, it's always relative. You always have to go relative to atmospheric or relative to something else, okay? So as you're increasing the volume that's available for air in the lungs, there's more space for the air particles. That creates a low pressure situation. Relatively speaking, atmospheric pressure is greater. Pressure moves from areas of high pressure to low pressure, and air moves in as we breathe, as we inhale. I see some glazed looks, some completely given up, and some going, yeah, I got that. So if you're in the glazed category, where can I start again to help you? Just picture those volumes. Go back to the cylinders. Picture the cylinders. Picture the cylinders increasing, except now it's our lungs. We've got a lot more space. which means that it's negative pressure relative to atmospheric, and air flows in. Okay, so as we're breathing in, pressure inside is negative compared to atmospheric. Negative is less.
The lung pressure.
The lung pressure is negative and the atmospheric pressure is greater.
Yes.
Okay.
Yep. Negative relative to atmospheric. So lung pressure inside the lungs is less than the atmospheric pressure. Yeah.
Is that related? I don't know. I'm just thinking of the Bernoulli's effect. Or you don't?
No, because Bernoulli effect has to do with the relationship between pressure and velocity, or pressure and speed. So we're really talking about pressure and volume. So I know as much as you love Bernoulli, he needs to stay out of this one. So just think about lungs expanding, creating more room, air rushes in because pressure here was higher than in here. Okay? Other questions? Other clarifications? Okay. Now, there is a way that you can kind of feel this if you're able to do it. What I'd like you to try to do is close your vocal folds. And one way to get to that point, if you just can't think about closing your vocal folds, is like a football move, like huh. And at the end of the huh, your vocal folds are closed. Huh. And then expand your rib cage. So close your vocal folds and right. and you suck in, exactly. Close your vocal folds and expand your rib cage. So I'm going to go huh. And then I expand my rib cage, open my vocal folds. Which way does air go? It comes rushing in, right? Because you had negative pressure. You had a big space. I don't want to know, do I? Can you get the feel for that? You almost feel like the vocal folds are being sucked downward, right? And then you open them and you create a negative pressure because you have a big space here. And it needs air. Okay? So it works if you think of this as during inhalation. So now we're going to go to the opposite extreme. And again, if we're thinking about just passive, quiet, tidal expiration, when you're ready to breathe out, all you do is relax. Okay, so you relax the external intercostals, you relax the diaphragm. As you're relaxing, what happens to the volume of the lungs? Volume of the lungs gets smaller. Okay, so as the volume decreases, pressure is increasing inside the lungs. So now, as the lung volume is decreasing while you're breathing out, you want to exhale, the lungs are getting smaller, pressure is increasing. Now the pressure inside the lungs is greater than atmospheric pressure, and air flows out. Questions? Now, when you're trying to kind of get this in your mind, remember not to think of the end points of inspiration or expiration. I find it much easier to get the concept as you think of, as you're breathing in, the lungs are expanding, creating negative pressure relative to atmospheric. As you're breathing out, the lungs are getting smaller, smaller lung volumes, higher pressure inside the lungs compared to atmospheric. Okay, if you think of it at the end point, you get all screwed up. Because it's at the end points where the pressure is equal between atmospheric and lung pressure. Okay? All right, so we know that most of the time, go ahead, I'm sorry.
Back to, when we're inhaling, is it the act of the rib cage expanding and that causes the lungs to expand and then the air comes in? It's not,
Okay.
I was kind of confused because I don't see how we can expand our lungs without air. I don't.
Right,
okay.
and you have to think of it as a simultaneous event.
Okay.
First of all, because of the pleural linkage, as you contract you're talking about breathing in, right? As you contract the external intercostals and the diaphragm, Because of the pleural linkage, they're pulling the lungs along with them. So now you've got a greater lung volume because they followed along. And as you're breathing in, that creates the change in pressure. But that didn't quite answer the phrasing of your question.
I mean, I'm having trouble wording it.
Oh,
just
you were
like,
going, do you breathe in first and then it rushes
yeah,
in?
yeah. So.
No, it's sort of like a continuous process. As you're expanding, the air is coming in. It's not, otherwise you get that sucking down effect like we did with, okay, my lungs are big and there's nothing there. So it's impossible to make them large without the air coming in. Yeah, so it's not a sequential event. Lungs get big, air rushes in. It's as they're expanding, the air comes in. Okay? Yeah, that's a good clarification because that's a confusing one too. Other questions? Okay. All right. You thought that was tricky. This is the first tricky class we've had. The relaxation curve. The relaxation pressure curve in old speech science books was one of the most horribly explained things on the planet. And I've tried to make it better by taking it kind of step by step. What we're leading into is how we have to manage the relaxation forces so they don't predominate when we want to talk. Because remember, we override everything the respiratory system wants to do when we're talking. And one of the things that we have to control are these relaxation forces. So the first step in the pressure relaxation curve is trying to understand at different points in the respiratory system what parts of the system naturally want to go back to REL. Okay? Now the first one, I have to admit, the very, very top here, when a person has breathed in as much as they possibly can, that peak inspiration of vital capacity. Some people who study respiratory physiology say that at that point, even the rib cage is beyond where it wants to be at rest. I have a really hard time visualizing that. But what this diagram is showing you is that we know when the lungs are highly inflated. Where they really, really want to be is their little collapse position, like they'd be outside the body. Okay? So their relaxation forces are in, I don't want to say in a negative direction, are in an expiratory direction. Okay? So when we think of relaxation forces, we're going to think about whether they are moving down towards REL. So relaxation forces moving down to resting expiratory level would be in an expiratory direction. Relaxation forces moving up to resting expiratory level are going to be in an inspiratory direction. So if you look here at the very, very peak, maximum inhalation where you've breathed in all that you possibly can, the relaxation forces of both the rib cage and the lungs are in an expiratory direction. And the easiest way to do this, and the way I always figure out relaxation forces, is to actually go there. Like take a giant breath and then just let it go. And it goes in an expiratory direction, right? You took in a huge breath, no muscle forces whatsoever, the relaxation forces took you back down. Okay? So here, this is sort of a mid-level. Don't worry about this one because it's not as clear. Here is, see it's labeled FRC here? This is REL. Cross that out and put in REL so that you know that it is resting expiratory level. And that's the point of balance. So everything is referenced to REL. When we talk about inspiratory or expiratory relaxation forces, that's relative to where the REL is in your body. So REL, we know that the rib cage wants to expand just as much as the lungs want to collapse. Okay, that point of balance. And everything else that we do in terms of relaxation forces or counteracting those relaxation forces is relative to REL. Okay? So here's the tricky one. When you're below resting expiratory level, so now go ahead and breathe out as much as you possibly can and then relax. Which way are the relaxation forces? Which direction? Inspiratory, right. So that's always the way to get oriented, is go to the extremes and then relax. And you'll figure out which way the relaxation forces are going. So if I've breathed out as much as I possibly can, I'm well below resting expiratory level. And the lungs still want to go smaller, but the rib cage is driven nuts. It wants to go back up. It wants to expand. So the relaxation forces are going to be in an inspiratory direction to get me back to resting expiratory level. So that's what the respiratory system naturally does. And the way to keep in mind is go ahead and take in a huge breath and relax. You have expiratory relaxation forces. Blow out all the air you possibly can. You have inspiratory relaxation forces going back to REL. Okay? The reason this matters is these are the forces that we have to counteract when we superimpose speech on the natural state of the respiratory system. We can't let the system work this way for talking, or I'd be going, and I have nothing to talk on. I'd lose it all. Or I'd try to go below resting expiratory level to keep on talking, and the system's going, nah, I want to be back up here. So these are forces that we have to counteract, and we have to counteract the relaxation forces with muscle forces. Okay, so the relaxation forces are passive. It's what happens when we do something and then just let it go. We need to counteract those with active forces to superimpose talking on this. All right, this illustrates the pressure inside the lungs, and I'm afraid this might be confusing with what we just talked about with volume. So if it doesn't work for you, don't worry about it. When we're at peak inspiration and the lungs are completely full of air, we have high or a positive lung pressure. When we have blown out all the air that we possibly can, the pressure inside the lungs is negative relative to atmospheric. And we're going to breathe in. Okay? High pressure to low pressure. But I find that graph can be confusing, so if you don't like it, don't spend a lot of time on it. Okay. Lung pressure is equal to atmospheric pressure at resting expiratory level. And the point at which resting expiratory level occurs in our body does matter a bit. If you picture that vital capacity curve, and you go, okay, that maximum point of expiration where I breathed out as much as I possibly could, I can't breathe out anymore. That's 0% vital capacity. And all the way up to peak inspiration where I can't possibly breathe in anymore is 100% of your vital capacity. Okay, so picture that curve from 0 to 100%. The point at which resting expiratory level happens isn't right in the middle. It's at 38%. It's kind of shifted downward a bit, lower than where you'd expect. So you've got a lot more options for breathing in than you do breathing out, relative to resting expiratory level. Does that make sense? So I think it's always tempting to picture resting expiratory level smack in the middle, but it's not. It's around 38% of your vital capacity. Okay, we've already talked about the low resting expiratory level. Pressure inside the lungs is negative relative to atmospheric. I'm sorry, go ahead. Or were you stretching?
No, I have kind of an off-the-wall question. Like whenever you're running and you get like the cramps in your side, what are those exactly? Like what?
No idea.
No idea? Really? Because I was always told that you're building up like carbon dioxide inside in your body, and it's causing a cramp.
I can never figure out why they happen where they do, though.
Yeah.
Does that make any sense?
I was always told to breathe out more.
Yeah, to get rid of carbon dioxide. Yeah. And part of that is probably true. Although I've never understood the concept of hyperventilation because it has to do with the blood gases, the relation of carbon dioxide to oxygen in your blood. So what you're trying to do is blow off more carbon dioxide. But how that relates to a stitch in your side is beyond me. You have an idea?
Well, I guess I'll comment on that one first before my own curiosity. But yeah, because I've hyperventilated before. But I was told to breathe into a paper bag because I was breathing too fast, so I was taking in too much oxygen. So it was, I guess, kind of balancing.
So if you're breathing into a paper bag, what are you breathing in?
Carbon dioxide.
Carbon dioxide, right.
And
again,
without the paper bag and you're breathing too fast, you're getting too much oxygen, you get lightheaded and pass out.
Right, and then you fix yourself. So passing out isn't a bad thing.
So, but my question was about yawning when you exhale.
Oh, you're going to start me going.
No. When you exhale from yawning, does it naturally take you below the resting expiratory?
No, because yawning takes you so far high in your vital capacity.
Right, but when you let it out?
Yeah, when you let it out, I'm pretty sure most people go back to resting expiratory level.
But it doesn't go below that?
Because you start using muscle effort. Yawning, you're tired, you're trying to relax. You're not going to exert muscle effort to go below resting expiratory level.
Okay.
But now you've maybe want to yawn, which is really a problem. So I'm sorry I don't have an answer for the stitch in the side. I'm sure it's in some pulmonary physiology book. And I'm fairly sure it has to do with the balance of CO2 and oxygen, but why it manifests itself that way never made sense to me. I just know it kind of makes people feel crippled and they don't want to go on.
Maybe oh no, I'm not even.
Yeah, speculation can just take us all in the wrong direction. Okay, so we've already mentioned that when we talk, it's these relaxation forces that we have to counteract. We cannot let the body do what it naturally wants to do, or we'd never get a word into our respiratory system. Now, the goal of controlling the relaxation forces isn't necessarily the one you thought it would be. What we are aiming for when we speak is to always have a constant subglottal pressure. We always want the pressure below the vocal folds to be relatively constant. And that is one of the main reasons, along with having the air to speak on, that's one of the main reasons that we have to counteract the relaxation forces. So if I breathe in a really big breath, and then I talk on it, and so at the big breath it's really, really loud, and then it fades out and it goes really, really soft. If people talk way all the time, it'd drive you nuts. So people expect a relatively constant intensity. And to have a relatively constant intensity for speech, you have to have a constant subglottal pressure. So the subglottal pressure for speech is measured in centimeters of water because it's a pressure measurement. And we'll talk a little bit later on how to measure this directly. But it's roughly 3 to 5 centimeters of water pressure. And that is the goal of the respiratory system. We always want to have a driving force of roughly 3 to 5 centimeters of water pressure for conversational speech. And we want it to be constant. So you can't let the system relax a little bit and then kick in a force to oppose it. It's almost like the breathing in concept. Things happen simultaneously. So as you get to different points in the relaxation curve, you need different degrees of muscle effort to counteract it. Okay, you getting that as a concept? So when I'm way, way up here, and I know I have huge expiratory relaxation forces, what kinds of muscle forces am I going to need to counteract that? What's going to counteract an expiratory force? Inspiratory force. Yeah, it's really basic and it's just the opposite. Okay, so you've got big, big passive expiratory forces when you're way above resting expiratory level. I cannot let that happen for speech. So I have to use inspiratory muscles, inspiratory muscle effort to counteract that so the rib cage and diaphragm don't just, so the lungs just don't squish all at once. Okay, so inspiratory muscle forces are going to counteract passive expiratory forces. And how much muscle effort you need depends where in the vital capacity curve you are. So how much muscle force as well as what kind of muscle force you need. Okay, so if I'm way above, I'm a singer ready to do this long 10-second thing that I have to sound gorgeous on. I took a huge breath. As a singer, I cannot waste all that air at once. To counteract the big expiratory relaxation forces, I need to contract muscles of inspiration. So I'm going to keep my diaphragm contracted. I'm going to keep the external intercostals contracted. And they're going to help me regulate the descent of the rib cage. Okay, so above resting expiratory level, you're trying to control the descent of the rib cage.
You use the inspiratory muscles for that?
You bet.
Okay.
Because you're working against expiratory relaxation forces. So you need inspiratory muscles to do that. So keep in mind the big inspiratory and the big expiratory muscles here, because those are the ones that are counteracting the relaxation forces. Okay, so let's picture the person who's singing this long, long phrase hits resting expiratory level and still has 5 seconds to go. So they're going to go sing, ah, and then they have to keep on going and going, and they're going, damn, I really should have breathed in more than this, and they keep on going longer than that, ah, sounding as beautiful as they can. What forces did they need? Okay, first of all, when they're down there, in what direction are the relaxation forces? Yeah, up. Inspiratory. Okay, so the relaxation forces are inspiratory. So to counteract them, so I could eke that last little bit of the phrase out, what muscle forces did I need? Expiratory muscle forces. And you can feel it. If you want to keep on talking or singing below resting expiratory level, that's when you feel your abs kick in. So the abdominal muscles kick in as expiratory muscles at that point. They really don't do much of anything above resting expiratory level. But once you have to force the system to go below or beyond resting expiratory level, you need the expiratory muscles to work against the inspiratory relaxation forces. Okay? Now the degree to which the strength of the counteracting muscle forces depends on where you are in the vital capacity curve. And when we look at speech, we'll see that we stay in a range that really doesn't require much muscle effort. We don't want to work hard to talk. So it's only when you're doing the extremes of a huge breath in so you can talk for a long, long time or sing a long, long phrase that you need a lot of opposing muscle forces. Otherwise, we're not working hard. You know, I'm staying in here and maybe I'm breathing in 20% of my vital capacity, which would bring me to 58% of my VC. That's not far above resting expiratory level. I'm not going to need huge muscle forces to work around whatever I do. I try not to go below resting expiratory level. So you can manage how much muscle effort you need, depending upon where you are in the vital capacity curve. Is that making sense? Okay, but to understand the concepts of the muscle effort counteracting the relaxation forces, think of the extremes. So when you're trying to figure out the relaxation forces, breathe in as much as you can and let it go. The relaxation forces will be in the expiratory direction. They need inspiratory muscles to control them. When you breathe out as much as you possibly can, way below REL, relaxation forces are in an inspiratory direction, and you need expiratory muscle effort to control them. Okay? All right, we said that. Any questions on that as a concept? Yeah.
So if you've run all the way home and you're out of breath and but you're trying to talk, like tell your mom your brother fell out of a tree or something, and you're gasping to try and catch your breath and you're trying to talk and your voice is just sort of all over the place, is that basically like these kind of your body's need for breath and these forces, and you're not able to counteract it effectively because your body needs air more than it thinks you need to speak?
Well, your body needs air, so you're forcing it to take in the big breaths that you use for speech. Right. I'm sorry, that you use to accommodate the oxygen that your muscles need. And it's really hard at that point when you say your voice is all over the place. That's probably the subglottal pressure varying a lot, because it's really hard to, after you've worked out or did a big sprint or ran home, it's really hard to go, okay, now I'm going to breathe quietly and controlled. So it's much harder to regulate subglottal pressure with that kind of catching your breath phenomena. Yeah, that would screw everything up. Well, it's one thing that actors have to deal with, and singers, because there are points in stage productions where people have to run across the stage or run in, and the guy I collaborate with in the School of Music, Joey Evans, told me that because he's really interested in physical fitness and how it affects opera singers' voices. And he said that one time he had to run across the stage, jump over something, and land on his knees and sing. And sound like, you know, a gorgeous tenor. And the coolest thing was, he said one performance, he went in and did the leap and he tripped. And he ended up sliding across the stage and then, you know, got up and sang. And the director said, well, that was so dramatic, you have to do it like that from now on. You know? So in some situations, and everybody noticed, like Pavarotti, who had this magnificent, huge voice, but he stopped moving on stage after a while because the movement would make him out of breath. And he sang great when he was solid as a rock and could just focus on breathing for singing. But as soon as he imposed exercise on it, he couldn't do it anymore.
When I'm nervous and I'm trying to talk, like I have that problem. Like if I have to get up in front of people I don't know or something like that, I have that same issue. And is that just like the anxiety, the physiological anxiety? Is
yeah, it's anxiety, and then you don't know what adrenaline does to the system. That screws everything up too. People tend to breathe more shallowly, so you're not going to have as much air to talk on. So yeah, it's better to get into the zen of talking and just be calm, cool, and pretend you enjoy it. Other questions on the relaxation forces? Okay, so for the next class, now there's 2 different instructions for you in the online class. For the next class, you guys need to bring a bottle of water. The online class needs much more than that. They need a bottle of water, a rubber band, a paper clip, and a 15-millimeter ruler. I know, I feel like it's one of those little 3rd grade class assignments where you go collect the things you need. Because what we're going to do is show sort of around the house way to estimate subglottal pressure. All right? Have a good afternoon, guys.